A data center is actively hostile to human survival communication. The architecture prioritizes thermal management and machine density, creating an environment that rapidly degrades the projection of sound. Massive airflow from computer room air conditioning units and the physical barriers of cold aisle containment systems actively mask human speech. They generate intense background noise and create dangerous acoustic shadows where sound simply cannot reach. Standard commercial public address systems fail under these conditions. To guarantee occupants receive evacuation instructions, the facility requires a hardened, code-compliant public address voice alarm system, a life safety backbone engineered specifically for high-noise environments. This legend establishes our visual language: red for fire alarm, amber for fire intercom, teal for security panic, and yellow for faults. A teal panic state operates under different rules than a red fire alarm. Blurring these lines introduces severe risk. This flowchart outlines the sequential logic required for a controlled emergency response. An input initiates the sequence, which the system must classify, prioritize into the correct message, route to the specific physical zone, and finally prove through timestamped logs. Surviving a data center fire relies on flawlessly executing the sequence. The system must translate raw detector data into prioritized, intelligible instructions while maintaining an unassailable chain of evidence. To understand how this logic operates in practice, we trace the signal path starting at the physical input phase. What actually happens the moment a manual call point or panic button is pressed on the floor? This diagram illustrates the one owner per path doctrine. Every input must report to a single, unambiguous system authority. We see three distinct, physically separated horizontal paths. The top red path is the life safety fire route. It is owned exclusively by the fire alarm control panel. When a fire input triggers, this panel holds the sole authority to initiate evacuation. The bottom teal path handles security duress. Panic inputs report strictly to the Security Operations Center, completely bypassing the fire logic. The middle amber path is the responder two-way network. This is a supervised intercom system owned by the Fire Command Center Master Station, enabling direct communication during a crisis. A frequent and dangerous engineering error occurs when these distinct paths are improperly integrated. Feeding security inputs into automated fire response logic compromises the integrity of the life safety backbone. This comparison matrix highlights the absolute rule of separation. Look at the must-not-do row. A security panic button must never trigger automated fire evacuation, gas suppression, or smoke control sequences. A red manual call point requires immediate automated evacuation and door releases. Conversely, a teal duress button triggers a silent alert for discrete security dispatch and CCTV call-up. Their outputs are mutually exclusive. Treating a security input as a fire alarm violates building codes and risks deadly false trip scenarios, including accidental suppression dumps and unnecessary full facility evacuations. We follow the approved signal path off the data hall floor and into the equipment room to dissect the physical hardware responsible for routing these isolated commands. This component architecture shows the flow of authority. The fire alarm panel transfers command status into the central voice alarm controller, which evaluates the priority table and selects the correct response from the message player. The controller then sends that signal to the power amplifiers. These amplifiers are the physical muscle of the system, pushing wattage through the copper cabling to drive the loudspeaker circuits across the facility. Because this is a life safety system that requires strict mathematical resilience, this engineering proof details the N+1 amplifier standby requirements. On the left, we calculate the connected tap load of the speakers, 132 watts. We apply a mandatory 20% design margin, bringing the requirement to 158 watts, dictating the selection of a 200-watt working amplifier. Moving to the right panel, we size the secondary battery power. We combine the 24-hour standby draw with the 15-minute active alarm load, add a 25% safety margin, and select a 65 amp-hour battery bank to guarantee operation during a total power failure. This hardware resilience matrix outlines single failure safeguards. The top right quadrant shows dual A-B speaker lines. This interweaved wiring strategy ensures that a single cable shear won't silence an entire data hall. In the top left, we see the physical implementation of the N+1 math. If a primary power amplifier fails, the system must automatically switch to the standby unit in real time, without dropping coverage to any critical zones. Furthermore, the voice alarm and intercom networks operate autonomously. They execute their life safety functions entirely independent of the general IT network or the building management system. Impeccable software programming cannot save lives if the physical hardware mathematically fails before the evacuation completes. Resilience is proven in the load calculations. During an active event, multiple inputs trigger simultaneously. If a recorded evacuation message, background music, and a manual firefighter page compete for the same speakers, the result is acoustic chaos. The system requires a rigid, hardware-enforced hierarchy. This diagram visualizes the voice message priority stack. Every audio source is assigned a strict tier. Notice the red Level 1 block sitting physically at the top. Level 1 is the live emergency page. An authorized operator using the command microphone has unrestricted priority. When they key the mic, it instantly mutes and overrides all pre-recorded Level 2 automatic evacuations and lower-level alerts. This cross-section shows how these prioritized messages are mapped to specific three-dimensional compartments. A fire event on Level 4 triggers an evacuation message only for that specific smoke control zone, while adjacent floors receive a standby alert, and plant rooms receive distinct instructions tailored to industrial hazards. We must now return to the extreme physical challenge of projecting these messages inside the data halls. This acoustic diagram highlights Challenge 1. Tall server racks and cold aisle containment physically block sound waves traveling from ceiling speakers to the technicians. Challenge 2 compounds the issue. The cooling units generate massive ambient background noise, operating at frequencies that actively mask human speech. Because of these factors, acoustic modeling is insufficient. The measurement mandate on the right dictates that field testing must occur under true operating conditions, meaning normal cooling is active and containment doors are shut tight. The mandatory metric for this field proof is the Speech Transmission Index for Public Address, or STIPA. It measures precisely how much of the original vocal signal survives the interference of the room to reach the listener's ear. An electronically perfect audio signal routing through flawless code is useless if the human ear cannot decode the instructions over the ambient roar of the server racks. Once the message priority and intelligibility are secured, we must define the escalation timeline. The system uses cause and effect logic to determine exactly when a localized warning expands into a broader evacuation. This escalation graphic outlines the timing logic. The progression moves left to right, from a T0 immediate response to a T-delta 3 full facility escalation. A confirmed fire, like a pulled manual call point or active sprinkler, triggers T0 immediately. However, other early warning inputs hit a T-delta 1 investigation timer, pausing automatic evacuation to allow the control center to acknowledge and verify the threat. This workflow dictates the response for early smoke detection, such as VESTA pre-alarms. The red warning rule at the bottom is critical. An aspirating smoke detector pre-alarm indicates particles in the air, not necessarily a growing fire. It generates a priority alert for operator dispatch and investigation. It does not trigger automatic facility evacuation unless explicitly configured in the matrix to do so. As the timeline escalates, the voice messages must synchronize perfectly with physical-mechanical outputs. This connected outputs diagram shows the fire alarm panel driving external interfaces. When the evacuate message plays, the system must simultaneously release egress doors, recall elevators to a safe floor, and activate smoke control dampers that exactly match the geographic boundaries of the spoken voice zone. Every second of delay in the timers and every mechanical interlock triggered requires documented, witnessed approval based on the facility's specific fire strategy. Arbitrary programming introduces fatal blind spots. While the public address system dictates automated one-way evacuation, emergency responders rely on a separate two-way lifeline. This diagram details the fire intercom architecture, linking the main command station directly to remote firefighter phones. This is a supervised bidirectional closed loop. It actively monitors its own copper cabling, immediately reporting if the line is shorted or grounded. It provides a secure, private communication path, completely distinct from the general PA speakers. The entire interconnected architecture remains theoretical until it passes statutory field testing. Look at Gate 2, the site acceptance test. This requires physical proof of audio levels, STIPA intelligibility in the data halls, and verified power transfers under load. This graphic outlines the integrated system test scenarios. We trigger a known source, verify the escalation timing, confirm the correct message priority, check the mechanical door releases, and gather time-synchronized evidence from the logs. Pay close attention to the security mandate at the bottom. Security duress scenarios undergo this exact rigorous testing, specifically to prove the absence of unintended fire outputs. Following handover, the facility enters the management of change loop to prevent operational degradation. The warning label at the bottom enforces a strict rule: never normalize a muted zone or a bypassed interlock without a documented restoration plan. The final step of any incident, test, or maintenance cycle is a verified, time-stamped reset authorized by the proper command center, proving the panel has returned to a normal, safe state. A true life safety backbone is built on immutable command boundaries, mathematically proven hardware resilience, and an unbroken chain of verified testing evidence.